All right, let's get started. So we're starting our last week of learning objective content today. Graphs are our last thing. There's, I guess, a reminder. There's no quiz or interview on graphs. Graphs is only assessed through task 8. So let's talk about task 8, which I already have open because the Wi-Fi is so slow. I don't feel like waiting for it. Task 8 is, I have mixed feelings about task 8. I think, this is the whole description too. It's a pretty short description. I have mixed feelings about this. I think task 8 is one of the easier tasks that I have you do. But task 8 does cause students quite a bit of trouble, more trouble than I expect. So there's some sort of disconnect between me and task 8. So as we're going through this content, if there's anything you can do that to explain like where that disconnect is and help me out. I've been updating my lectures over the semesters, and it's gotten better. But there's still a little bit of a disconnect between, I think, me and the students. So if there's any question of how to do task 8 that doesn't make sense in lecture, let me know and we'll talk about it. So let's go over what task 8 is, or your last required programming task. I think that's the disconnect, though, unfortunately. The empty seats and people who don't pay attention. I think that's the only thing it really can be. For task 8, we have this degrees of separation class as a constructor that takes an array list of movies. And we're just worried about the array list itself, the array list of movies. It's not really what I want to say, but we're not concerned about the ratings of the movies. We just want the titles and the cast lists. And we're not concerned about songs anymore either. We're just doing movies for this one. And then once we have that constructor with the array list of movies, we have one method to write. So this is a pretty straightforward explanation of an assignment. But the coding gets a little trickier. I'll say the testing is actually fairly straightforward in this one as well. But the coding is where the true challenge is of this one. Degrees of separation is the one method we want to write. This is going to take two strings as parameters that are going to represent two cast members or two actors in these movies in the data. And we want to return their degrees of separation. I always trip up on the explanation of degrees of separation. I'll do my best here, but I also link to the Wikipedia article here. Degrees of separation is the number of movies that you have to traverse to get from one actor to the other. So we have two actors, and we want to define their degrees of separation with, I'll start with the base cases, if it's the same actor as both parameters, so the degrees of separation from an actor and themselves, we don't have to traverse any movies to get there. We're already there. Degrees of separation, 0. If the actors are not the same person, and they've starred in a movie together, there is a movie that was given in the constructor in this array list. There is a movie where those two actors have starred in a movie together. Their degrees of separation are 1. You traverse just that movie. And then to increase the degrees of separation to get the higher ones, if they're in a movie with somebody who is in a movie with someone who's in a movie with someone, how many movies do we have to traverse to get from one actor to the other with the minimum number of movies? So for example, if two actors, actor A, actor B and actor C. If actor A and B were in a movie together, actor B and C were in a different movie together, and actor A and actor C were never in a movie together, then actor A was in a movie with actor B, who's in an actor with movie C. The degrees of separation would be 2 because we had to cross over 2 different movies to get from actor A to actor B. And if you've ever heard of the degrees of Kevin Bacon, that's exactly what we're doing here. The degrees of separation between Kevin Bacon is known as an actor's Bacon number. And it's this whole thing, I don't know, people do. But that's what we're doing here. If somebody has a degrees of separation to Kevin Bacon of 3, their Bacon number is 3, and actors play this game, they try to lower their Bacon number. And people try to find the path. You come up with an actor and try to find that shortest path, bless you, between that actor and Kevin Bacon. Yep. Mm-hmm.
Have those actors' names.
Yeah, in different movies. They shouldn't be in the cast list for a single movie more than once, but they could be. That shouldn't break your algorithm. None of my testing does that. If you want to test for that, it's fine, but I won't test for that. But they will be in the cast list of different movies in the same data set.
And I need to have like A and B in the same movie. Let's say like for BBC, next one, A and B, third one, A and C.
Yeah. Yeah, and you should come up with some good test case. I want to talk about testing for a bit on this one. Like, you should at least have that test case that I just said, like A to B to C, and a degree of separation of 2. Because there's one of the big, you know what, I'm actually going to get a little dangerous here. But I got to refresh my memory on what the incorrect solutions are for task 8. Because I'm pretty sure my incorrect solutions are pretty weak. Like, at this point in the semester, let me focus so I don't leak anything too bad. Hey, what's up? I didn't choose it. I don't know. I think it's Kevin Bacon's been in so many movies with so many different people. I think that's why. But that's what the game ended up being. So always distance 1, that's just a completely broken one. Bad when not connected, that's checking your edge case. If the 2 actors are either one of them's not in the data set, the movies that you gave, or they're just not connected, it should return -1. So that's testing that. Doesn't find shortest path is the trickiest one here. Self distance not 0, that's another edge case. So doesn't find shortest path is the trickiest one. And if you get lucky on your first test case, you can get that one out with pretty crappy testing. 3 of these you should get, like, those should be no problem. This is the only one anyone should ever struggle with, or else you're honestly just not trying. But this, now somebody's going to call me out in office hours. If you do come up with some where you have good tests and you are not getting through one of those, we'll talk about it. I'll help you through it. But yeah, this is the only one. But you can get through this one. Doesn't find shortest path. You absolutely should have a test case for this. But let's talk about this a little bit. I got to finish my sentence from earlier. Hold on, I'll get there. That at this point in the semester, I don't have incorrect solutions for everything. Like some of the earlier tasks, I have a wide array of incorrect solutions with every possible bug that could ever happen. And you can't get through the testing part of Autolab without a pretty solid test suite. And then as long as your code is passing your test suite, you're going to get through my tests, no problem. Because there are incorrect solutions for all the bugs you would have written. You had to test for them. You run your tests. You find out that your tests fail your code. You find the bug. You fix the bug. You run the debugger and all that stuff. That's early in the semester. That's what I try to do, is have lots of incorrect solutions covering every mistake, pretty much every mistake that I've seen students make. That's my goal. I don't go too overboard with it, so I don't hit the really intricate, unique bugs, because I used to do that, and oh my goodness, it was a mess. But at this point in the semester, later in the semester, I back off with that. I don't have incorrect solutions for absolutely everything. Test 7, I think I have quite a few. But I try to have fewer incorrect solutions later in the semester, because at this point in the semester, you should be used to writing good test suites, and I need to back off to really test if you are writing good test suites or not. Are you coming up with your edge cases, all your common, uncommon, all that stuff? Can you do that without me holding your hand and having Autolab slap you on the wrist and say, no, you need more tests? Can you just write good tests on your own? That's where you need to be at. Because, like I said last time, 250 and 220 did start requiring some testing, but not a lot of testing. But after 220 and 250, I'm not aware of another course that tests your tests at all. So in a semester and a little bit here, you need to be able to write your own tests and test your own code with no hand-holding at all. That's where we need to get you. So you're not spending countless extra hours on those 300 and 400 level homeworks, courses with homeworks, because you've never learned how to test. So that's where you need to be at. So at this point in the semester, you have more questions of my tests pass in Autolab, but now I'm failing on your tests. Those are more of the office hour questions that I get. these days. And that's by design because I'm not holding your hand with the testing. This one, especially so, doesn't find shortest path, does require you to have at least some form of testing. And what this does incorrectly, I'll leak this one right now, which I did in the other section, but I didn't pull it up and name it by name, is you should have at least one test case where there are multiple paths between two actors of different lengths. So if you have a test case, I would have a test case with at least like 5 movies and at least 5 actors. And for at least one of your test cases, have 2 actors where there's like 3 paths of 4 connecting those 2 actors. And somewhere in there, there's 1 path of 3, something that really challenges your code. What this one does is when there's multiple paths, it doesn't find the shortest one. I'm pretty sure I coded it to explicitly find the longest one. So we'll find the longest path between 2 actors, not the shortest one. So any decent test case should get rid of that one, even if you have pretty crappy tests overall, and then you'll get your code failed on my tests, and that's where you're expected to, add more tests that you're not forced to add. I know no one will ever do that, but that's what you're expected to do. Let me rephrase that. Anyone who does that doesn't come to me in office hours because they can find their own problems at that point. If you just write more tests that you don't have to write, I can't stress this enough, you will save many, many hours of your life that you won't spend just bashing your head against autograders. Just write your own tests. You'll find your own bugs. You'll be able to fix your own bugs. And you won't have to spend your entire life getting this degree. It really can make that big of a difference. So write your good tests for this one. The test cases I don't think are too hard to write for this one. So let's go over writing test cases. You can create your test files like we did in tests 6 and 7. Or since this takes an array list of movies, you can manually create your array list as well. I find it usually easier to create the test files and then use the file reader methods that we already wrote from task 6, the read movies method. You can count on that one being correct in the correct and incorrect solutions in Autolab. So if you want to use that method to just load up the data into an array list of movies, go for it. And then use your data files to organize your data instead of building this big array list of movies. Can be a little bit of a pain. And then your test cases, manually go through your data, or better yet, manually construct your data in a way that creates the test cases that you want. And then when you call degrees of separation, since this just returns an int, this is the big part of what I mean that test cases are easier to write with this. It just returns an int, so you assert that that's the int that you expected. This is no longer, it returns a data structure, and the data structure might be in any order, so you got to go through. We're done with that stuff. I had you do that. I'm not going to have you do that on every single assignment. This one just returns an int. Make sure it's the int that you expect, and that's it. So if it returns the int you expect, it passes your test. If it doesn't pass your test. And you're manually verifying these with the test cases you create. I would not use the entire movies.csv file. Don't use all of that data because it's going to be a nightmare going through it all and finding your test cases. And that data isn't complete. I have this big note here to emphasize this point. The data isn't complete, so if you say actually know the Bacon number of your favorite actor for some reason, well, I shouldn't say for some reason. If you've actually played this game before, you might know their Bacon number, but that might not be their Bacon number in this data set because the data set is incomplete. So don't get in that trap of knowing like the real life answers. You are. Like, you can't look at his code. You know that, right? You're not even paying attention in lecture. You're talking, distracting other people, and you're cheating. You can't do that. Like, you know that, right? It's rare that I have to go out in the crowd like that. I almost never have to do that. All right. So that's testing for this one. I would not just use test cases from the data. Normally I like using real life data, but for this one, if it helps you make your test cases, it's better to kind of make up the data. So you can create your test case based on, I want a test case, like Jesse said, where there's multiple paths of length 4 and one path of length 3. I want to make sure I have those test cases in there, so you can kind of make up names and everything and get your test cases working the way you want to get those different situations. One, I would start with a test case, kind of your barometer test case, where it's the actor A, actor B, actor C, like I said. And if you're failing that one, and 2 actors in the same movie, the same actor named twice, actors who aren't connected at all, obviously all those test cases, your edge cases and all that. But the trickier ones, I would handcraft those to be exactly what I want them to be instead of trying to use real movies and doing it that way. So any questions on this test and how to set this up? Oh, there are a few other examples. That came up in the other class. The links between websites, how many clicks would it take to get from one domain name to another domain name? That's the degrees of separation of websites. You might have heard of that one. And they say the degrees of separation is at most like 6 between, the number 6 keeps coming up. 6 between any domain to another one. You're 6 clicks away from any website, or infinite if it's a website that can't be accessed. Then there's the degrees of separation between actors, of course, Bacon number. I've heard there are just researching for this task, that there are some really unknown actors with Bacon numbers of 7, but they're far and few between. Most actors are 6 or less. So they say the 6 degrees of Kevin Bacon, you're at most 6 movies away from Kevin Bacon if you start in anything ever. And then between people too, that you're 6 degrees of separation away from any other human being on the planet. If you, between you and anyone else ever, or maybe has to be alive, I would assume, that you know someone who knows someone who knows someone who knows someone, 6 degrees of separation, anyone on the planet. Which is just crazy that how networks work like that. I'd assume that number is even less now that the internet's such a big thing. There aren't a lot of office hours this week? Wait, like this week specifically, did a lot of TAs cancel? Can I show up to office hours using the whole movie file for your tests? Yes, unless your question is, why am I failing a correct solution? Then I'll just say no. Yeah.
So as a extreme test case, we should have up to let's say 6, 7 movies, and then a bunch of cast names.
Yeah, I would. Yeah, and then your test cases have multiple test cases, multiple pairs of actors, and if some of those pairs have multiple paths, and making sure that your code does find the shortest path. So that's the biggest bug that I find, and that's why I used to not even have that one test, that incorrect solution that I pointed out, because that's the biggest bug that I do see. So I'm like, well, I better add an incorrect solution for at least that one. Is somebody codes up test cases where there's 2 movies and they do the A, B, C thing that I described. Make sure that the degrees of separation is 2, fine. And then they come to office hours and say they're failing my test, and that's like the only test case they have. They're like that, and then the -1s and the 0s and stuff, and the 1s. That's the most complex test case they have, and their code's just absolutely broken and garbage. And they didn't pay attention at all in lecture. On Wednesday, by the way, the reason, I'll get back to this, but I almost forgot to say this. This is pretty tough. This is a hard task. This is going to be the hardest task that you've done all semester. The reason I say it's an easier one is because on Wednesday, I walk through step by step and really hold your hand on how to code this one up. I explain with diagrams and everything. I don't show any code, which might be where the disconnect is. I don't show any code, but I show diagrams and I explain this part of the diagram looks like a hash map. This one, you should use a queue. This one, probably an array list. And that's actually where I lay them out on the slides. I'm seeing it in my head there. I walk through, this should be a loop, and I basically explain what the code should be, but I explain it in lecture. I don't expect you to get this problem statement and be able to code this degrees of separation method. That'd be way too big of an ask for 116. So I do walk you through exactly how to solve this one. and but then students will have the most complex one is the ABC, and then they fail my tests. And it's because their code's absolute garbage. They didn't follow along with that lecture. They just tried to code it on their own or have something else code it for them, and it didn't work. Then my answer in office hours is like, well, you need more test cases than that. So having good, thorough test cases is going to suss out all those bugs that you could have. But with a very weak set of test cases, it'd be hard to do this one because the only information you're going to get is failed my tests. And my test names are degrees of separation easy and degrees of separation medium, I think is what I call them. Like, it's not going to help you. The names don't help you at all. Again, at this point, you should be able to write your own tests. Okay, now, any other questions? Did I answer your question? I forgot what the original question was. It kind of went off on a tangent. Okay. All right. Anything else before we get into slides? Yes. Thanks. Yep.
I heard it was a rumor, but I heard it like in the upper levels that Ethan Blanton has a religion now or something like that.
I wouldn't doubt it. What did you hear they worship in this rumor? They were.
It's like at the front he says like a quote or something like that, and they're like, "Oh man, that's so true. That's right." Like all the people at the front are like this.
I want to know what the quote is. Wait, the quote you said or cult?
It's like
Because it could be either.
He gives advice every time my roommate was telling me, and I was like amazed at it. I never knew.
He does give lots of advice. Yeah. I wouldn't be surprised if we start in a religion. If anyone, I don't know if it's worth repeating, but if anyone didn't hear. The religion of Ethan, if you hear about that, I wouldn't be surprised if it's a thing. It's probably a cult, just throwing that out there, but but he'll call it a religion. Yeah. What's coding have to do with religion? Ethan has everything to do with religion. that came out wrong. That could be way misconstrued. But if a lot of y'all, I assume most of y'all haven't met Ethan Blanton yet, but he's one of the 220 instructors. You've at least registering for 220 seen his name. I won't spoil anything. You can meet him. It's he's don't be scared of him. He is super passionate about computer science, and he has opinions that he'll let you know about dramatically. I love the guy, by the way. I'm not saying any of that in spite. Like Ethan's the best. His passion is palpable. And when you do see him, tell him I said IDEs are the best. He will not use an IDE. So, but in 220, you should use IDEs for sure, just because they're useful, and it'll annoy him. No. 220 and distributed systems. They don't what? What was it?
My friends in 115, they don't use IDE.
Oh, they do kind of. Well, they use that online IDE. I forget which one they're using now. Replit? Okay. Yeah, and it's an IDE. It's an online IDE. It's not as powerful as IntelliJ for sure, or PyCharm. But in 220, Ethan will suggest Emacs, which is just a text editor. And he would kill me if he heard me say just a text editor, but yeah, we got off track last time. Let's not get too far. We did finish early last time, so we had a little bit of time. But we got to get through these slides. So graphs is going to be the answer for our degrees of separation problem. Today, I'm going to every OS on Earth. Oh yeah, anything. He has his technologies that he is very passionate about. And if you don't like what he likes, make sure you let him know so you can argue about it. It's fun. Yeah, Notepad++ is way too much for him. It's Emacs, or not too much, but too. I don't know what the right word is. Too little, maybe. But graphs. In this content today, I'm going to introduce what graphs are. This should be pretty much of a low-stress lecture because most of you are in 191. I'll still introduce graphs for those of you not in 191. But if you're in 191, a lot of this is review. It's just kind of a laid-back thing. And then Wednesday, that's why we're going to go through the excruciating details of breadth-first search. I say excruciating because I'm going to go through, like I said, how you would code it, not just the over-level idea of this is kind of what breadth-first search is, but exactly step-by-step how you're going to actually use breadth-first search to accomplish that degrees of separation in task 8. So let's introduce what graphs are. Let's start with a review of the data structures we have. So these are the data structures we have, 4 of them. Why do we need a 5th one? Like, why are you even going to bother? So let's talk about the ones that we have. We have 2 sequential data structures. Our array, which for this class we used an array list, which used an array under the hood and just gave us some extra functionality like being able to pretend that we can resize an array. And I was careful there. I did not hate on Emacs, just so you know. I was just saying I'll defend IDEs. But Ethan will defend Emacs to the death. And linked list is our other sequential data structure. Sequential meaning that order matters. If you put values in an array list or a vanilla array or a linked list, you expect those values to be in that specific order that you inserted them, or inserting at specific indices of an array list. You expect that order to be preserved by the data structure. Then we moved on to key value stores, which are not sequential. This is where you want an associative data structure. We want to associate certain values with certain keys. And we did that with a key value pair, and order no longer mattered. We get these values in any order that the language decides or the implementation of the language decides. They're ordered by the hash value of the keys using some hash function that we're not necessarily privy to. I believe it's the hash function of the object in Java, but I'm not 100%, because even if you don't give it because we have a default hash function. The hash function from the object class, that method that we inherit, I believe it's that, but I could be wrong. It might do something else when we use a hash map. And there are other key value stores that aren't based on hashing, but that's the one we use this semester. And trees, our first nonlinear data structure. Trees gave us the idea that our data is not linear, it's not sequential, and it's not associative either. We kind of have this extra dimension in our data structure, and this gave us a lot of efficiency. We get to take advantage of that powerful log n. And we said if we have 1 million nodes in a binary tree and it's balanced, then let me reword that. Each layer we go down a tree, if it's a complete binary tree, each node has either 2 or 0 child nodes, or I don't feel like redefining balance because I messed it up there. But if it's fully balanced, each time you go down a level in the tree, you're doubling the number of nodes that can be represented. So it's an exponential increase in number of nodes as you go down the tree, which means we have a logarithmic height to a tree with a certain number of elements n. So if we have 1 million nodes in a tree, it's about height 20, which is extremely powerful. If we have 1 billion nodes, it's height 30. 1 trillion is height 40. Every time you add 2 more zeros in decimal, it's only 10 more nodes, 10 more height in the tree when it's in binary. So a very powerful data structure if you want efficiency. And when you have this nonlinear structure, if you have a decision tree where you're making decisions based on the value of a node, we did find for BST, where we're going left or right based on a comparator. But a more an application of that, I should say. An application of that would be an actual decision tree for AI. Thinking of like AI in a video game and like a first-person shooter. Each node is going to be a decision node or an action node. The first node might say, am I in proximity of the player? If yes, is the player shooting at me? If the player's shooting at me, I'll take cover. If they're not shooting at me, maybe I'll shoot at them. And if I'm not in proximity of the player, I'll patrol. And making decisions based on each node to figure out what actual action they should take. That can be done with other data structures, but a lot of that structure is probably going to be in your code itself. With a decision tree, you can create all kinds of different decision trees for different enemy units and throw them all in the same method that says, run this decision tree. It gives us a lot of power having this nonlinear structure. And then we're given data like this. And I say those are the 4 data structures you know. Store in memory all of the subway stations and connections in New York City, or all the intersections and roads in Buffalo, or the example that we're going to spend the most time on, we're going to build this graph, all of the early connections in the internet, all the early internet locations and their connections. And we look at the 4 data structures we have, and none of them really make sense. This definitely isn't sequential data. It's not quite key value pairs. So our best guess with what we have, our best attempt is going to be to use a tree. And of course, the answer is going to be graphs because that's the theme of the whole week. But let's try using trees at first to see where this breaks down. So we'll pick one of these nodes. I'm going to pick UCLA as like the root node to the tree. And then all of the child nodes are going to be every node that's connected to UCLA. And this, well, mind you, this won't be a binary tree. It'll be just a generic tree because I can have more than 2 child nodes. So I'm going to have like an array list of child nodes. And for each child, we're going to have their children be the nodes that are connected to this node. And with Stanford, that's SRI and UCLA. So UCLA and SRI. And we see a big problem immediately. As we go down this tree, we're going to have UCLA has Stanford as a child, which has UCLA as a child, which has Stanford as a child. We're going to keep zigzagging back and forth on this connection. Now we can get a little smarter with this and say, well, let's just not go to the parent node. Like, that's silly. Let's not do that. And then we still have the question of what do we do with SRI? We could go through the whole tree and figure out that SRI is in the tree, so let's just not add that one either. But then we lose the information that Stanford and SRI are connected. Where do we put Stanford as a child of SRI, or SRI as a child of Stanford? Either way, we're going to have duplicate data in this tree, and we're going to have a lot of these decisions of like, where do we just keep adding extra nodes over and over? I'm behind on chat, but I don't know if I'm missing anything either. Ethan has connections in industry. I'm not in industry, though. That only matters to me if I want to go into industry someday. I don't think I want to. So let's do something better. So instead of adding SRI as a child node to Stanford, let's add a connection to the existing SRI node. So whenever we find a node that's already in our data structure, let's create that connection over to the existing node. And now we've deduplicated our data. We don't have any duplicate nodes in this entire thing, which is great, but it's not a tree anymore. We can't call this thing a tree. So let's call it something else. We're going to call this a graph. A graph is like a tree, except the big difference is that graphs can have cycles. Trees can never have these cycles where we can travel from one node back to that node without repeating any nodes with at least 3 total nodes. So like just going back and forth doesn't count. But once we can introduce a third node and go around this path, call that a cycle. Yeah. Sorry, can you repeat that?
What's the relation between all the nodes? What's it just for the sake of deduction?
The relationship between these in this data, that means there's a connection, like there's a physical wire connecting these 2 sites, and then they can send information. This is, did I not introduce this? This is the early days of the internet, before it was even called the internet. It was just these locations, these universities, and they had physical connections between each other that they could send information over. And that was it. That was the entire internet. I believe this is in the ARPA days, before it was called, it was either ARPA or DARPA. I think it was way back in the ARPA days, before it was the internet. This is the very, very early foundations of the internet. So this means from UCLA, you can directly send a message to these 4 universities, but there is a path from UCLA to MIT, so you could send your messages there. Yeah.
So graph always have an way like one node to back without repeating it?
Not always. So can you always go from one node and then back? That's your question, right? without repeating. Yeah, so I do have to add to this. I mention it, but I don't have it in the slide. But there should be at least 3 nodes to call it a path. Depending on your specific application, too. Sometimes this is called a path. But for my purposes, I want to call this a path. Or else we could use trees and get away with it. But you can't always do this. This is what we call a bidirectional edge. And that's the graphs that we're going to use in this class. That's what they're going to be. In this example and in the homework, and those are the only 2 graphs we're going to see. They're going to be bidirectional edges, meaning we can travel the edge in both directions. But there are directional graphs where the edges are only in one direction, and you would only be able to go in that one direction. And then to represent an edge that's a bidirectional edge in a directed graph, or even in our graph, bless you, we would have to represent it as 2 different edges to represent that we can go there and back, which we actually will do in our code. And there are cycles. So a tree can't have cycles. As soon as we have a cycle, it's not a tree anymore. But every tree is actually a graph. We're going to represent them different in our code, but we can take anything we represented as a tree and represent it the same way in our graph. We can represent that same information in a graph. It'll just be a graph that happens to not have cycles, and that's fine. But trees cannot have cycles. And the big problem here, the reason why this can't be a tree, is our algorithms are going to get all jammed up. We're going to run a traversal algorithm. Say we want to run a pre-order traversal. We're going to start with UCLA. We're going to visit this node, go to one of its child nodes, visit this node, and then make a recursive call on one of its child nodes, visit this node, make a recursive call on one of its child nodes, visit this node, make a recursive call. As soon as we find a cycle, we're going to get stuck in it forever and go infinite. So a tree traversal algorithm, the way that we have them written, is not going to work for us here. We need to do something better. So let's do something better. We're going to change the way we represent this. So even though this is a node-based data structure, it's still nodes and they have connections. We're not going to represent this the same way that we represented linked lists and trees, where we had separate node objects in memory, and those objects had references to other node objects. We're not going to do that. We're going to have a separate graph class that stores all of this data in one data structure. It's actually going to be a hash map of values to array lists of values, and the values will be a generic type. So just to foreshadow that a little bit. But what we need to store are nodes and edges. We're going to have one data structure that keeps track of all of the nodes and edges in the graph. And this is why graphs, it made more sense to kind of just cut the graphs memory diagram and interview, because they behave in our code a lot differently than the other node-based data structures. They really are their own beasts. So nodes, every node, these are very similar to what they were in linked lists and trees. I just said we'll represent them differently, but in theory, they're the same idea. There's something that stores some value. So this is a node with the value Stanford. And then edges are representing connections between them. This is what used to be references. In linked lists, it was the reference to the next node. In trees, it was the reference to the child nodes. Here, we're representing those links a little bit differently, those edges a little bit differently. They were still edges in linked lists. Actually, a linked list is a graph, too, for what it's worth. They are still edges in linked lists and trees, even though we didn't call them that. We said references. But we're going to represent them a little bit differently here. And this is how we're going to represent this graph. So this doesn't really help us in code. This is a nice visual for us humans with eyeballs. The computer isn't going to be able to read that without a ton of coding and computer vision and image recognition and everything. This isn't helpful. This is something we can represent as a hash map, where the keys are the nodes, the values of the nodes specifically, and the values in the hash map are array lists of all the nodes that are connected to that node by an edge. This is how we're going to represent our graph. For those of you in 191, this is an adjacency list. Actually, even for those of you not in 191, this is an adjacency list where we're going to store lists of all the edges connecting each node. And for what it's worth, every edge will be in this adjacency list twice, because we're a bidirectional graph. We're a or an undirected graph, I guess, to be technical on it. For example, UCLA to Stanford and Stanford to UCLA. The edge is in this data structure twice to represent that we can go in both directions on that edge. If this were not an undirected graph, if it were directed, we could have cases where like UCLA to Stanford you can do, but not Stanford to UCLA, and we would just remove UCLA from the list here, saying that that's a one-directional travel. Like in downtown Buffalo, if we were representing those intersections as the nodes and connections between those intersections, the roads, as the edges. Some of those roads are one-way roads. We would only have a one-directional edge connecting those two intersections. And here's all the code. And you can, I still saw a lot of students not using the BST code. Just a reminder, any code that I show in lecture or give in the examples repo is fair game to use on your homeworks. The intent on task 5 was that you would take the BST class that I gave you, copy it, and just plomp it down in your data structures directory. In your ratings.datastructures, I expect to see BST class right there, copy and paste it from the examples repo. I saw a lot of you taking, which is fine, by the way, taking the insert method and manually rebuilding the functionality of the BST. That wasn't my intent. You get a little more practice that way, but it was always frustrating when somebody had questions in office hours where they copy and pasted that wrong, which I still don't even know how that really happens. But or maybe they didn't know they were allowed to copy and paste it, so they typed it up. But I mean, it was obviously my code. I don't know. I don't know what happened. But the graph class, it's in the examples repo. You can take that whole class, copy the entire class file, and paste it right in your data structures directory in your code. And then in your degrees of separation class, you can say new graph. Private graph of string equal, whatever you want to name it, equals new graph of strings. Like, you can just use that class. There's no need to rewrite these methods at all. If you want extra practice, go for it, knock yourself out. I'm not going to stop you, but there's no need for it. That's not what I'm testing you on with task 8. Task 8, I'm saying, can you populate the graph? Can you call add edge and, with the correct pairs of actors? And can you traverse the graph using breadth first search to find the degrees of separation between two actors? That's what I'm testing you on. You don't need to recreate this. We don't need to bother with that. But let me explain what this is. How we're going to store all the information is a hash map of a generic type to an array list of a generic type. And that type is going to be string for this example, and it happens to be string in task 8 as well. Those should be your actors. And we're going to add bidirectional edges, meaning that we can traverse the edge in both directions. And when we call add bidirectional edge, we're going to add nodes for both of those values. Adding a node is going to be lazy initialization. If it's the first time we've seen the node, initialize a blank array list for that node, for the adjacency list, and then add to each node's adjacency list the other node. So we'll get that edge information in the adjacency list. Running this code, getting all of those edges added to our graph is going to give us exactly this information in that adjacency list. It'll give us exactly this adjacency list. Yeah.
So inside the array list, would that be like our edges?
Yep. Mm-hmm. Yeah. So this is our hash map of, what was my n? My hash map of n for node, I guess, of n to array lists of n. That's what this is in the code.
Okay. And within the array list are the actual edges. So that would be our adjacency list, right?
Yeah. Yeah, well, the whole thing is our adjacency list. Oh, and I forgot to finish my sentence earlier. For those of you in 191, what I meant to say was that you also know about adjacency matrix, where we're only going to use adjacency lists. This is how we're going to represent our graphs. If you want to code an adjacency matrix, by the way, I'm not going to stop you. But the code I'm giving you is going to use an adjacency list. And other than this, I'm not going to mention adjacency matrix. But if you want an adjacency matrix, you would create an array list of n. And then it's a two-dimensional data structure, just like a matrix, where the rows and columns are all of the nodes. And then there's a one or true in each cell if there's an edge connecting those two nodes. And in a bidirectional graph like this, the matrix would be symmetric. And I'm done talking about adjacency matrix. All right. I'm just going to begin talking about paths. So path in a graph is a sequence of nodes where each consecutive pair of nodes are connected by an edge. So UCLA, SRI, Utah, MIT, BBN, RAND. This is a path in the graph because each consecutive pair of nodes were connected by an edge. SRI, Utah, BBN is not a path. Utah and BBN are not connected by an edge, and they were a consecutive pair of nodes in the path. Not a path, or what would be a path, the sequence of nodes. It is a sequence of nodes in the graph, that's fine. It's not a path because it's not connected. Not a path. Not allowed. I'll be using that. I just want to make sure we're all on board with this definition. I think this one's a pretty straightforward definition, I hope. But I'm going to be using the word path a lot in the upcoming lectures, so let's get that definition out there. And then breadth first search. This is the one algorithm we're going to use for graphs, and this is the one you'll have to code up. So let's introduce what it is. I'll go through this in much more detail on Wednesday, but let's at least introduce and get it on the table what breadth first search is and why we use it. One, finding connected components. I'll talk about connected component in a second, but even more basic than that is how do we visit every node in a graph? It's the same problem as traversals with trees. I want to visit every node in a graph exactly once. So I want to make sure I don't visit a node multiple times, and I want to make sure I get everything covered. How do I do that? And a little more complex, how do we tell if a graph is connected? A graph is connected if every pair of nodes in the graph are connected by a path, and two nodes are connected if they're connected by a path. UCLA, I can find a path to Harvard, so they are connected. If every two pair of nodes are connected, connected graph. If we remove a few edges here, this graph is no longer connected, but it is still a graph. It's a graph with two what we call connected components. So if we have this graph, how do we tell if the graph is connected or not? And well, with this graph, we're just going to use our eyeballs and just look at it. Well, it looks like two separate connected components, not connected. How do we tell if two nodes are connected? Well, UCLA, let me just try to get over to Harvard. I can't get over there anymore, so they're not connected. But the internet's a little bit bigger these days. So the internet looks more like this, and I'm not manually looking at this at all to try to figure out if two nodes are connected or if there's some link out there, some IP address that's on the deep web that I can't access by clicking links. I'm not going to stare at this and figure that out. So we're going to need some algorithms to get us this information. And that's where breadth first search is going to come in. Breadth first search is going to do everything for us. It can even do path finding if we don't do any more, but we are going to get degrees of separation, connected components,